Pascal's principle states that the pressure applied to an enclosed fluid is transmitted undiminished throughout the fluid. And this principle is very important for hydraulics. This is a hydraulic. I've got two pistons, and I've got this liquid that's completely enclosed in the hydraulic. And so the idea is you apply force to one of the pistons. Typically it's the smaller one, but it doesn't have to be. You apply force. This is called the input force. And the piston, of course, pushes the water, and the water is going to push the other piston. And so this is the output force. Now, because of Pascal's principle, the pressure that exists here at the input has to be the same as the pressure over here at the output. So that means the pressure for the input has to equal the pressure for the output. And we know that pressure is force over area, right? So pressure equals force over area. Therefore, this is the force on the input equals the area of the input piston. So this would be the surface area that this force is applied to. That has to equal the output force over the output area. And of course, that'll be the surface area that the force is applied to of this piston. Now, typically this formula is rearranged so that we have the output area over the input area. And we set up the forces as well. And this is the formula that's in the content for this unit. And what it shows us is that we can amplify forces without using motors or electricity, anything like that. All we're doing is taking advantage of Pascal's principle. And so I have my input force. If I want to get more force out, in other words, a bigger output force, all I have to do is change the size of my pistons. I need to have the input piston be smaller than the output piston, as we have in this example that I drew here. This piston has a bigger surface area than this one. So this force, the output force, will be bigger than the input force. We're amplifying forces. This is what happens in most cars. A lot of brakes are hydraulic brakes. And so when you push on the brake pedal, that is the small piston. Right? And that pressure is transmitted undiminished throughout the hydraulic fluid to the output piston, which is essentially the brakes clamping onto the disc there to slow down the car or even stop it. So this is how Pascal principle applies to hydraulics. It comes straight from this idea that the pressure is applied to an enclosed fluid and it will be transmitted undiminished throughout the fluid. And it is key that the fluid is enclosed. If there's a leak in here at all, then this pressure is not transmitted undiminished, and that can have a huge impact on how well the hydraulic works. So you don't want to have any kind of leaks. Additionally, this fluid that is here for hydraulics, as far as I know, it's always a liquid. Maybe there's some exceptions I'm unaware of, but it doesn't have to be. It could be a gas, but for hydraulics, we use liquids, is my understanding. We use what we call hydraulic fluid. It's low density and also low friction, which is important, of course, to have low friction so that very little thermal energy is generated. No leaks, and you want a low density, low friction liquid in here. And of course, we choose liquid because it's incompressible. Now, the other thing to bear in mind is that we're doing work. Whatever this input force is, it's pushing this piston, work is being done. Well, I know from conservation of energy that whatever work I put in here, I have to get out over here. And I know that because there's nowhere else for the energy to go. So, what does that look like? And I should say I'm idealizing here. I'm saying that there's nowhere else for the energy to go. Maybe there is. Maybe there's some thermal energy generated. But the ideal case is that the input work is going to equal the output work. And we know how to calculate work. Work is FD cosine of theta. Remember, theta is the angle between the force and the motion. Well, here I'm pushing the piston down. The piston's going to go down, in other words, in the same direction as the input force. So this is going to be 0, and the cosine of 0 is 1. And that'll be the case here, that the force and the motion are in the same direction, and here, because this is going to go up. So the force, the output force, and the motion of the output piston are going to be in the same direction. So cosine of 0 is 1. That means that I just have my input force times the distance that the piston moves. That has to equal the output force times the output distance. And we could rearrange this formula just like we rearranged the other one. And it'll look something like this if we do that. And notice how here the word output is in the numerator up here, but it's in the denominator here, okay? As opposed to in our original equation here, they were both in the numerator. So why is that important? Well, that tells me that the output force is quite large, much larger than the input force here, but the output distance, the amount of distance this piston is actually going to move, will actually be smaller than the distance that this piston moves. So that's kind of the trade-off. Yes, we amplify the force, but the piston isn't moving as much. So a little bit of a trade-off there, but still, hydraulics are very important in our society. We use them in lots of things for heavy machinery. So we use them in cars, construction vehicles, airplanes. They're used all over the place, very important. And it all just comes from Pascal's principle. The pressure applied to an enclosed fluid is transmitted undiminished throughout the fluid.